Okay, here we are. So I think we can start with the correction. So thanks again, Glenn and Andrew, for being with us.
Yeah, no problem. So we're here to wrap up our discussion of the EDS module in Plumed. And I had put together some exercises that are pretty short and straightforward. I don't know if Avi, who's here with us, tried them, but I'm going to walk through what I put in the tutorial and some Jupyter notebooks, which I'll post afterwards from the data, and also a little bit of the scripts that I wrote in case that's helpful. So let me jump over to browser, and Andrew will chime in if I did anything weird. So this is the masterclass tutorial that we made. We have these giant pictures that I'm going to fix afterwards by hopefully shrinking the pictures. And to remind people, the idea that Andrew told us about last time is that our system is represented by a potential or Hamiltonian U, and we want to modify it in the smallest amount of possible so that it matches an average value of some variable f. And so the way we do that is we take this EDS module and we say that we want our observable to have a particular target value. And the main thing that we need to know is how often do we calculate the average of that observable in order to update a bias parameter. And so I can show what that looks like. Any other comments, Andrew?
No, I think that's great.
Okay, so first we're starting with a 1D model. In this workshop, I used the PES, potential energy surface MD function of Plumed, which I assume Giovanni or someone like that wrote once upon a time. And it's an MD code that does Langevin dynamics in 1 or 2 dimensions. So to start with 1 dimension, we have an input file that looks like this. It has a temperature, which is 1, so that things are in kind of reduced units, a time step, a damping coefficient for Langevin dynamics, and then we run some number of steps starting from some position. This is a random seed. It doesn't matter if the system is periodic because it's harmonic, so goes to infinite energy anyway. And then we load some Plume file, and for PESMD, it loads a Plume file which both defines the potential and also can do the biasing in the same file. So what I did for here is I wrote a script called run PESMD. Don't know if this is helpful for people, but it loads the appropriate plumed on my cluster. It takes an input file like the one I just showed, a plumed file, and an output prefix. And then it replaces these variables, prefix and plume file, in the input file and the plume file so that I only have to run the script to actually execute the PSMD, which looks like this because it reads the input file from standard in and then writes to an output file and also to the terminal. And then let's see. So to run EDS in 1D, do something like this. This is what's the example on the website. So we have a harmonic oscillator, 1/2 kx squared, and I made k 10. That seemed to give good results as an example problem. And then the way that PESMD works is it uses a distance between 2 fake atoms, 1 and 2, and you can break it into components so that you have d1.x, .y, and would have .z in other systems in Plumed. But we can bias this x coordinate d1.x to using this math eval function. This ff is a function, then by this bias value adds the potential to the system. And then for EDS, we want to make this x position have an average of 1 instead of what would be 0. And I chose a period of 200 steps to sample in, but you could vary that. And then it writes out to some file and some temperature. And the last thing to note is this bias scale parameter which we mentioned in the first talk, makes it so that the system is actually represented like this, lambda times f, whereas in the other, in the original implementation, it would have been lambda times f divided by target f. Okay.
I have a question there, Glenn.
Yes.
So is that correct then that the potential is defined by both the FF term here and also your input file to the PS?
This is the input file. In this case, I'm using this as the input file to PSMD. So I maybe missed it that there's a harmonic 1D. This would be the just running a harmonic oscillator.
Uh-huh.
So this defines the potential, which then then runs on,
Okay.
and then it prints out. That's unbiased. Forgot that one. And then you can add EDS to shift it.
Got it.
That is actually what's going on. Oops. In this here, which now I have to. Maybe I will. Guess shouldn't have done this yet. So that's what's being shown in this image. So if you run an unbiased simulation, it will have an average of 0. If you add, I missed one. If you add a harmonic bias by using the restraint function, which adds some kind of harmonic 1/2 kappa x minus 1 squared to the system, it will change the average and the mean. It will shift it up, but it won't get all the way there. And if you use our EDS bias, then it will go all the way to 1.0. And if you follow the moving average of that bias, you'll see that over some number of steps, the system starts sampling around 1.0. And then you can histogram. I took the second half of each trajectory just to be safe. And if you histogram the results, the unbiased you'll see is a nice thing centered at 0. And I also plotted and asked people to plot the ideal histogram, which is a Gaussian with standard deviation KT over kappa, it turns out, and that fits perfectly. Then if you add a harmonic bias to the system, it shifts it, but you can see that it both shrinks the standard deviation and it also doesn't make it all the way over to 1 because the average of a sum of Gaussians doesn't, you can work out what the average should be, maybe numerically, and it would not get all the way over. But with the EDS bias, you can complete the square and have exactly a mean of 1, which is the target value, and then the standard deviation should be very similar or only moderately affected, I guess. Right, Andrew? Maybe it's the same exactly.
It should be the same. Yeah.
It should be the same, yeah. It looks the same, and it should be because it's just completing the square in that case for 1D. So then, any questions about that, Avi or Giovanni or Andrew? More comments?
One question. Can you write out sort of like what the final value of your biasing parameter is somewhere?
Yes. So this is a good time to look at the output. Great points. So we can output in 2 ways for EDS. One is the regular Colvars file. So this is printing time, the position, X, there's nothing in Y and Z because it's 1-dimensional. FF is the value of whatever we said, 1/2 K, whatever. And this is the actual bias number. So those are the same. This is using this print star thing. So anyway, this is the bias, the force from the bias, and the coupling value is the linear parameter that's being added. So to shift it to the right, I think it's supposed to have this minus sign. And then it goes down. We talked about how when you load it in, you can use the average or various things. So we also have, maybe it's not in this one. Yeah. I'll show later that we also have a restart file, which contains some of the internal stuff that's saved so that you can exactly continue these simulations. But you only need the Colvars file to see this biasing parameter. And I think that's shown here. So that's the next thing, which is that what I asked people to do is to try to find which column that is in the Colvar or restart file. And you see that it starts at 0, and then as it calculates an average, it shifts over time, and then it kind of plateaus. So we could say it's maybe converged after around 4,000 steps or time units, actually. And then in this other plot, what I did is I wanted to show we understand what the actual bias being applied is. And so it turns out that the bias that's in the bias column is actually like lambda x minus x target. And if in the original one, if we hadn't put bias scale equals 1, then it would have had this divided by x target like this. And so you can, from the Colvars file, you can confirm by plotting this or the bias column that it's being calculated correctly.
So I remember Andrew saying that part of the reason you took out that over x target scaling was because if it's 0, you have a problem. But as long as it's not 0, presumably it's sort of fine because then the coupling parameter will account for it.
Yes. Now I realized that it was there when I went to 2D and I made a mistake. So I'm gonna can say what that is right now, which is an interesting point that I wanted to bring up. So for this 2D position, it's the same. Let's talk about that. So for 2D, by the way, in the input, you just need a slightly different input that has an initial position in X and Y. And to tell it that it's two-dimensional, in the in here, you just have to add a Y. And then what I did with this 2D potential, where I wanted to target change X or Y to have a certain value, the first thing I did was I moved X to the right because that's what I'd done before. Then I said, oh, I'll move Y down and make center -1. And that actually caused a problem because in the original version, because it divides by the target, it then flips the sign of the bias from what it should be. So the original implementation actually caused a confusion with signs as well. So it's not impossible to choose a bias, but you had to be more careful about what you put in as the input. So for example, a way to do it would have been to make the collective variable that you're biasing, instead of d1.y, it would have been to make d1.y some positive number instead of -1 by like adding 3 or something. Then you could have set the target to 2 and then d1.y would have been -1 or something like that. But that's seemed a little silly, and that's why we ended up adding this factor and not and mostly using this implementation. Right, Andrew?
Yeah. I mean, the whole thing is like, when we started this project, like we wanted to get rid of the sensitivity to the units, right? Like if you did this with nanometers versus angstroms, it would change everything. So the first, I mean, what is standardly done in this kind of setting would be to divide by the variance of the collective variable, because the variance would account for the unit change. But then to divide by the variance, we'd need to know the variance a priori. And if you were going to try to estimate the variance, and then you've like got this confusion that your like variance would be sensitive to your simulation. So then I thought, okay, we'll just divide by the mean, which in all the examples that we had done was quite reasonable. But then after we got the paper out, like somebody pointed out, what if you want to set the collective variable to be 0? And then I realized that was a problem. So then we ended up putting this bias scale in there. So basically, if you set the bias scale to whatever you want, then you have to realize you're sensitive to the unit system. Although that was originally in PLUMED 1, where Plumed 1 used the units of the MD engine. Now in Plume 2 has standard units, so this is all no longer a problem. So if you do set the bias scale, you don't need to worry about units because Plumed has standard units. So there's a fun history lesson.
Well, you can choose the units in Plume, so I guess in Plume 2, in addition to
yes, you could make a mistake.
The MD engine standard, so it does change around. But anyway, you can set it so that it's always, you know what it is, and be careful about it. Yeah, but I guess you're saying you would actually, if you wanted it to be unitless and have the prefactor just be in energy units, then you would divide by the standard deviation. And if you wanted to have it in as like a force constant, you would divide by the variance. And either way,
sure, yeah,
it would have, those would be positive numbers, whereas the setting the mean or normalizing by the mean has the issue that you said.
Yeah. Just
zeros.
You just run into a problem that like you don't know the standard deviation a priori. So
yeah, but it did make sense. In terms of, I actually don't even have it here. I just guess I'm using the default of the prefactor for the learning algorithm, and that's where this really mattered for realistic systems, because there's one more parameter which you can say like, oh, it starts at 10 kcal per mole per watt. And then as you change units, that learning parameter in the old version, we could say, oh, like 10 is a good value for anything because it was already scaled. But now, if you are doing some massive complicated CV, then, maybe you need a really big bias. And if it's, whatever, as we were saying. Okay, so 2D is, as I said, it's pretty much simple. I showed one more complicated example here, which is one where instead of biasing, here I still biased the single collective variable, but I made a new one called x times y, and it changes then the skew of this distribution. So I thought that would be interesting to show. So now it's basically, it's quite different from the other situation because it doesn't just shift the mean of the variable. It does shift the mean of the variable that I chose, x, y, but if in terms of x and y, it's now changed the means and the variances and everything, and it's a totally different potential at this point, basically. Which may or may not, depending on the kind of scenario you're in. That's something to keep in mind. Could be good or bad. Okay, and then I went over to closing these things, a molecular system. Oops. Alanine 2, I could have chosen more complicated systems, but I wanted something that could run in a reasonable amount of time. So here I took this alanine 2 input from the previous masterclass. We all know that we can define two dihedral angles, and now we can bias it to have some other value. Here, maybe there's more importance of choosing the period carefully and so forth if you want to bias more things. I showed a little bit briefly, which I thought was interesting. This is a 2 microsecond trajectory of alanine 2 in vacuum, and it doesn't sample this other minima, which we would get if we did metadynamics or something. If we say that we want phi to be equal to 1, then it samples, interestingly, a lot more space in order to get that to happen. And if we say that we want psi to be equal to, no, this is probably phi 1 and this is probably psi 1. Yeah. And I can check that. Yes, this is phi equals 1. So phi equals 1, it suddenly finds this other minimum that was there before, or metastable state. And by sampling in that state, it basically can satisfy this psi equals 1. Whereas if you want phi to be 1, it now finds some weird balance between all of these states. And you can look at how the bias changes. And then I tried to bias phi and psi together to both be 1, and the system, and it crashed. So that's where what I wanted to get in, talk about, or we talked about a little bit in the other video, which is that as you try to bias more complicated CVs, you have to be careful about applying a bias too fast and make sure your learning rate is matched to the system. And then it also may not be possible. There could be impossible values. So I don't even know if it's, I think that it should be possible to have psi equals 1, phi equals 1, because you would just sample over here. But, you know, the path to getting there was causing the system to crash. So I need to do a little more experimenting with that myself. And
yeah, you know, one thing that can happen in these systems that are vacuum is a lot of like the EDS, an EDS adds energy to the system when it's finding the bias. So it's some kind of non-equilibrium. I mean, over time, the learning rate stops changing. And so over time, it will asymptotically look like an equilibrium calculation. But if you do a system that's in vacuum, you can have some real bad problems with the thermostat. Either it doesn't bleed energy fast enough, or it can have like, if you're doing like velocity rescaling, was this CSVR or was this Langevin?
Langevin. No, I actually don't know. I take it back. I would have to look at the input of this thing.
Yeah, because you can have like, because that's such a low degrees of freedom, you can have weird modes in that as well, which might be a problem.
Yes.
But in general, if you're insolvent, things seem to work a little bit easier, I think.
Yes, we'll have to test and see if that works better. I just wanted something that could run very fast. This is was many tens or hundreds of microseconds per day, I think.
Yeah, I'm this fast.
So that was good for sampling, but bad for crashing. Okay, I think that's what I wanted to say about that. You can try some things I mentioned at the end that you could try besides taking other systems, is to try biasing more than one at once. Try using these other parameters that we have in here to get it to work. Namely, Andrew mentioned we can use this pressure thing to regularize the parameters that it chooses, so it's more likely to find a stable solution if you do it multiple times, which is something that's in his review article. And to combine, if you're combining multiple CVs, you can try doing this LM or COVAR, or you can try changing the fraction of CVs that are updated at each time, which is this multi-prop thing. And you can also try changing the this poorly named range parameter, which is the prefactor for the learning algorithm, as well as especially this the time scale. Where was that one? Pace?
It's period.
Period, yeah. So those are the things to experiment with. Any other thoughts about that, Andrew?
Maybe one or two interesting things that can be done as well is you can have dynamic set points. So there's the center arg variation, so that you can bias the system to something which is itself a collective variable. Now this at first may be confusing, like why would you ever want that? One thing we use this for is if we're loading up the set point programmatically. So like you want to load the set point from a file, or you want to load the set point from some other calculation, you can use that. Another interesting one is I don't know if you already mentioned it, Glenn, but basically stopping the bias with a freeze. So if you're really trying to do like a nice, if you're trying to use this in a scholarly publication, it's rather than trying to rely on the bias equilibrating, it's better to just run it for so long and then freeze it. And then you have that bias and you can do whatever, go on to production or other calculations, and you could just load the bias. Although of course, if you leave, you don't have good sampling in your equilibration, that can change. So you should always check to make sure your CV is indeed back at the mean. But
that's what I actually meant to check, to check.
Yeah.
But I didn't have time to do it, which would be to take this system, for example, and it'd be interesting to freeze the bias and then run metadynamics, which would only take 20 minutes, 10 minutes to converge, and see if it is indeed found a bias that makes the mean equal to 1, or if it is just stuck.
Yeah, although when you do metadynamics and EDS, you need to be a little bit careful, because if you're biasing that collective variable, right, you shouldn't expect the mean to still be there.
No, but if it's fixed, I mean fixed bias, and then you do metadynamics, and then you calculate the mean from the e to the negative.
Oh, sure. Yes, absolutely.
Yeah, I think it should be. I mean, it probably won't be, because realistically, you'll then sample more. You might sample more states than went into this bias. So probably it won't be exactly right.
Yeah, I think, if you this is like something you brought up in your talk that's really important, is that biasing to match experimental data is a separate task than enhanced sampling. And so like any kind of enhancement you get, like what you showed in the previous example, is accidental. Or I mean, like it's related, but like you shouldn't be using EDS to get enhanced sampling. So all of the caveats that you have about sampling still apply with EDS. It's just a method to tune your force field to better agree with experiments without needing to go through a very lengthy iterative process of changing all your force field parameters. Or it's great for approximating things that can't be represented, like missing components of the system, or maybe when you add salt to the system, or when it's annealed, some properties change. You can kind of capture that with EDS instead of trying to phenomenologically model it exactly. Cool. The only thing I did want to mention, Glenn, that you had in there is, did you talk about how you're calculating moving average?
Oh, like how the algorithm's actually doing it?
Yeah, because sometimes you'll select your plot. Can you go back to the 1D example?
Oh, yeah.
Or maybe you already closed it. Just
No.
show any of those plots that show convergence. Yeah, like right there. So that plot right there, is this really a windowed moving average, or is that like a cumulative average up to that time point?
This is a windowed moving average, I believe.
Okay.
I mean, I calculated it, but I'm telling you that I believe it's like 100 frames averaged together. That's moving along, not a cumulative average.
Yeah, so that's one thing that is important to note in EDS, is that EDS is meant to make it so that the ensemble average is equal to the set point. So if you do computer running average, it may not look like you're matching it. In this case, obviously it's fine because it's a very simple system, but there can be cases where, like, if you look at even if you look at the moving average or something, it looks like it's not matching the set point. But what you want to do is look at the whole, trajectory average to make sure it's matching, because it can be in systems that are very slow, or you have a very long period. You may not be matching it, every 500 frames.
Right, that's true. But it also, the beginning part it has to be thrown out, or you should freeze.
Yes.
You really mean after you freeze and you run for a long time, it should match on average. Although isn't the way that it's sampled over a fixed period and then it gets reset?
In principle, but like one of the things about the algorithm is that you can have a system where like it cycles like this, and the lambda will also cycle with it. Mm-hmm. Right. And so it can be that like it doesn't ever match it in any fixed like frame. But if you look at the whole average, it does match it. And the algorithm that we use in EDS, like it's not really just gradient descent. It's like a particular variant of gradient descent called like follow the regularized leader. And one of the things about the algorithm is that the guarantees on its convergence are on the average value. So whenever you freeze, you really should take the mean. And so but in general, it's not a big deal, because that idea of taking the mean and that freezing it and that you need to look over the whole system is just for kind of pathological cases where you have a period that doesn't disappear or dampen out. But in most MD simulations, as long as you have solvent, you're not going to see periods like this where you never quite match it until you look at the average. Does that make sense, Glenn?
Yeah, something to keep an eye on.
Is there anything that it needs to be to sort of have that dynamic behavior that you couldn't get it to like properly, like to converge solidly to, is that fundamental to the approach or?
Yeah, so I think so I think it's something like there can be cases where it appears that it doesn't converge whenever you look at like a fixed window, or like the bias is always going to be oscillating. It does have a dampening, so it should eventually dampen to zero. But there can be cases where like you'll see just way better performance once you freeze it and take the mean, or you'll see that the performance it converges slowly if you watch the individual bias value, but it's actually converged when you take the full system mean. We definitely will see that. Like you'll see, like if you're looking at lambda over time, you'll see something that looks like, you know, like this, and you look at that and be like, oh, it's not converged. But if you actually just take the average here and run it with that, it'll actually look great. So that can be something where the convergence is actually better than it appears. So that's why I usually tell students working with this method to not really look too hard at lambda over time. That's not as indicative of convergence as it is like a plot like this. Like this shows you really if you are converging. But yeah, you know, like I think the examples that Glenn has shown you here are the worst examples for convergence. Like you can have bad convergence here when you're in vacuum or when you're in a one-dimensional, two-dimensional system. That's when you see the worst performance. Usually once you have a solvent and a good thermostat, everything just kind of dampens out and smooths out. It's not that big a deal.
Yeah, I think the harder problem, well, not harder problem, but I mentioned in my other talk that I think things that are like properties of liquids and things are better because there's many molecules that have to satisfy that value. Whereas when I did the coarse grain directed simulation on a protein, and it could take hundreds of nanoseconds or something to switch between two states that have different values of the thing you're biasing, that's when you can get into trouble also.
Yeah, that's true. That's the whole ergodicity thing. Yeah. That it's harder when you have to sample them all.
Yeah. Okay, any last thoughts or questions?
Thanks for putting this together, Glenn. It's a lot of work. It's very constructive though.
We will try to update the figures so they look better on the website, and people are always welcome to email us and ask about the method. You can see from these examples that surprisingly it still worked, even though you know, we implemented it quite a long time ago, but pretty much everything worked out of the box, which was good to see.
I guess I do have one question, which is only tangentially related to this particular example, which is in terms of trying to match, say, distributions. Was that in the example somewhere? I'm sorry, I didn't get a chance to go through them.
Yeah, so there's two versions of matching a distribution. One is like that's well, I could have done something different, but that's why I tried matching like a higher order moment of this distribution in a sense by showing this x times y. But you could also do something like match the changes of variance, or the, like for a Gaussian like this, you could you don't have to bias very many moments in order to fit like whatever you want. Or you could make this non-Gaussian by adding other, you know, other terms in, basically like making it have a cubic average, a cubic moment equal to something. But what Andrew talked about, and maybe he wants to just mention the other paper that he wrote with James Dama about biasing distributions. And now there's other methods that do similar things.
Yeah, I think that, so we wrote a paper in 2015, I think, about how to make metadynamics converge to a specific distribution. So metadynamics normally converges to a flat distribution, like you flatten out your free energy surface. And then like the complement of that is the free energy that your system was without a bias. We showed how you can converge to any arbitrary shape. And we did some fun things like use it to edit you know, the alanine dipeptide example to look like a picture of the University of Chicago logo. We also did one where like we have a system which has a radial distribution function, and we edited a piece of the radial distribution function. So we just edited like one of the peaks so that it's a little bit wider. So you can kind of do fun things like that. And then I think it's called variational enhanced metadynamics is a similar idea. It's like more things like variational enhanced metadynamics has like more things going on, but one of the things you can do within that framework is target a specific distribution. I'll say about that method though, is that it's very like finicky. Like you have to be really careful about boundaries. Like if you're in a periodic system like alanine dipeptide, it's usually easier with a period. But if you're trying to do things like edit an RDF or edit a specific part, you'll have all these problems of boundaries. And if you don't deal with the boundaries, you have problems where like your system, because you're doing metadynamics, it will eventually push you out of the boundary of where you want to edit. So I think in general, if you're going to try to change the distribution, what Glenn mentioned is a much better starting point, is to take the shape you want and turn it into a series of moments. And then you can bias, like we did a paper where we biased the first 4 moments of the radial distribution function of water. And that was enough information. And you don't have to think about boundaries. You don't have to think about like convergence like you would, because to do the targeted method, you're trying to do metadynamics. And so you have to think about things like how fast you're adding hills, if you're doing well-tempered. But if you can't get it with 4 moments, and that can happen where you want to do some very sophisticated editing, then you can use our approach. It's the target keyword in the metadynamics package in Plumed. But just so you know, like you need to turn the distribution you want into like a PMF. And so we have a script. I think it's somewhere on the metadynamics documentation. We have a script to turn something like an image or like an X-ray scattering function into a distribution which you can bias to. And you can read our paper from 2015 that talks about some of these details. But I think a better starting place is just to bias moments. It's really simple to do, and you don't have to think about units or converting to a PMF or normalization, things like that.
Yeah, and just to point out the other things Andrew was talking about, there's a VES module, Variationally Enhanced Sampling from Omar Balsin, that has a target distribution thing, and it works differently from metadynamics because it doesn't add Gaussian hills. It tries to learn some coefficients in a basis set. And then now there's this OPES, which I believe was the subject of a master class, a few weeks ago, which I've played around with a little bit, and I believe OPES also has a version where you can target a distribution, but I'm not 100% sure on that. Yes, so that's for people might be interested in that. And I guess, Andrew, in that case, once you learn the bias, you fix it, and then hopefully it works in the same way as EDM.
Yeah,
caveats.
That's right. Yeah, one of the things that James and I always argued about on that method is that, like, provably it's going to give you worse enhanced sampling than metadynamics. Like, because you're not flattening it, you're not getting ideal enhanced sampling. And so that means that, like, the farther away you are from a flat distribution, the more poor your sampling is. So then all of the same caveats we had about EDS, like, apply here. For example, like, if you want to make one state be much more favored, then you change your system so you're much more favored in that state. That means your sampling will be then affected by that, so that you're not getting good sampling everywhere, so that your change to the PMF to sit in that state might be wrong. So that then when you go on to do some other thing, like, I'm assuming that your goal is not to fit this distribution because you already know what the distribution is because you're fitting it. But like, if you're going on to do some other property, you may have the same kind of sampling problems that you would have in EDS, and they might even be worse, because when you're editing a distribution, you're setting exactly what the ratios are everywhere, whereas the EDS is a minimal biasing method, right? So it's like trying to change your system as little as possible. Anyway, I don't know. I think it's cool. Like, we used it for some cool work. I think it's interesting, like, if you have a scattering function, like, exactly what the distribution should be. It's, I think, useful, but in general, I think it's kind of a Pandora's box because of you are going to introduce new sampling problems or new sampling issues when you start editing the PMF explicitly.
Cool. That was very helpful. My main takeaway from it, like we've sort of got some things we're looking at where we have for some reason, like a data distribution that we want to match, but we basically have to to do any of these things, we essentially have to characterize the data distribution into some kind of collective variables or moments, and then you can apply these various methods.
Yeah, I think that's the best place to start, is to fit the moments. If you do have something though, like you just can't fit it even after you fit like 4 moments, or you run into problems like the system's exploding because the moments, like as you get to higher moments, the derivatives get bigger. Then yeah, you might need to switch to something like target in metadynamics, or as Glenn method, there's more modern metadynamics variations that will maybe give you better convergence or better behavior. You can do that, and you may, but I think you end up with a lot more hyperparameters, you might say. Like you have to think about the boundary, you have to think about is it normalized correctly. The other thing too is that when you get like a scattering function, you have some data, it can be that, like, for example, you have negative values or you have some noise, and your noise might be innocuous in your data distribution, but then when you go start trying to bias it, that noise might be ridiculous, right? Like it might, that kind of, maybe you would just have a little bit of noise here, but then when you try to match that with metadynamics is going to try to hit every single little bit of the noise there, right? And you can start having weird effects happen. So it's possible, but I think that the more fine structure you try to fit, the more I don't want to say headaches, but like the more things you need to start thinking about.
I think with that, I think we can wrap it up. We can hit this button. I don't know if I can stop. No, I think Giovanni has to stop the streaming if he's available. Otherwise, we can log out. Okay, he's going to stop streaming so we can close up.
Thank you.
Mm-hmm.